In this video, I'm going to talk about matter what it's made up of. So we got to start with the law of conservation of mass. So scientific laws are things that always happen. They don't have an explanation. The theory is the explanation as to why. Theories evolve over and change over time, but laws are things that always happen. Like gravity is a law, right? If I drop something, it will fall. So the law of conservation of mass, conservation means it stays the same or is conserved. This is, or states that mass, okay, mass is neither created or destroyed. It is just rearranged. So more specifically, mass is neither created nor destroyed during ordinary chemical reactions. Oh my goodness, can't read that. Here we go. So it just gets rearranged and put into other forms, but it's still all there, even if we can't see it. So what is matter made of? If it's being conserved, what is it made of? Well, it's made of 3 particles. So subatomic particles, sub means below, okay? Below the atomic level. So we're talking about what is in an atom. So an atom is the smallest building block of matter. We talked about this with elements. Elements, the smallest piece of an element is an atom. If you look at what's inside an atom, it's not just that particular element anymore, but there are 3 things that make up an atom, and you may have heard of these. They are protons, neutrons, and electrons. Okay, so protons are, we use the lowercase p when we're talking about protons, and we usually give them a little plus. Okay, and we'll talk about why in a second. Neutrons, an N, give it a little 0 up there, and electrons, E, lowercase e with a negative. So location-wise, protons and neutrons are both in the nucleus. And the nucleus is the center of the atom. So if I draw a little picture down here, okay, this part in the center, I'm going to color it in, okay. This is the nucleus, center of the atom. So protons and neutrons are in there. Electrons, however, are not. Electrons are surrounding the nucleus. So I'm just going to write for now, actually we'll be more specific, orbiting the nucleus. And it's kind of like planets, like in our solar system. The nucleus would be like the sun, and the electrons would be like the planets orbiting around. Okay, and you've seen pictures or even drawn them yourself like this. All right, so how big are these things? Now, by how big are they, I really mean to say how small are they? They're very tiny. We can't even see an atom, let alone a proton, a neutron, or an electron, okay? So actual masses, here's the thing. You don't need to know what they actually weigh or what their actual mass is, but let's write it down just to get an idea. A proton is 1.673 times 10 to the negative 27th kilograms. A neutron is 1.675 times 10 to the negative 27th kilograms. And an electron is 9.109 times 10 to the negative 31st. Okay, so you don't have to know these numbers, but what I want you to notice is this. Look at the proton and the neutron masses. They are really similar. Like that negative 27 means that decimal right there is going to move 27 places to the left, making this point and then 26 zeros 1673 versus point 26 zeros 1675. Like they are almost the same. So when we're talking about relative mass and relative charge, that's where this comes into play. Relative means not your cousin, not your aunt or your uncle. It means compared to. So relative mass means compared to each other. A proton and a neutron are essentially the same size, the same weight. So I'm going to put 1 for them because they're so close that they're basically the same. Okay? Whereas an electron, that negative 31, that means we're moving our decimal 31 places to the left. And I know you're like, well, 27 places is a lot, so is 31. They're kind of close. Not really. That's a huge difference. Every time we move over a place, it's a factor of 10. So really, the difference there is 4. That's 10 to the 4th. That's the difference. All right, so an electron compared to a proton and neutron is super duper tiny. So its relative mass compared to the other two is basically 0. Like it doesn't actually have no mass, but basically 0 compared to. Be like a dime, the mass of a dime compared to a gallon of milk. Okay, a dime basically weighs nothing compared to what a gallon of milk would weigh. All right, relative charge is the same thing. We could actually measure their actual charges and the units and all that. Like they have a positive or a negative charge. Relative means compared to each other. So protons are positive and electrons are negative, but they're positive and negative the same amount. So if you have 1 positive proton and 1 negative electron, it will cancel out. Like if I have to pay you $5, but you owe me $5, that difference is 0. So they would cancel out. So a relative charge of positive 1 and negative 1. Now a neutron has no charge, so its relative charge is 0 because it doesn't have any to begin with. All right, so we've got our protons, neutrons, electrons. You can see where they are. Their relative charge and their relative mass are the kind of the main takeaways. It's this column and this column. This is not something you're going to have to know. I just wanted to use that to illustrate the relative mass.